Good morning, class. Today I'm going to cover the topic of pipelining hazards, and let me take the example of RISC-V architecture. The RISC-V architecture supports 5 stages of pipelining. The first stage is the instruction fetch stage. The second is the instruction decode and register read stage. The third is the execution of those operations and calculation of address if required. The fourth stage is the memory access, and the last stage is the write back registers to write back to the register for the execution of the data. Now there are obviously improvements if we consider pipelining, but at the same time we need to consider the situations in which the instruction cannot be executed in the next instruction cycle. So basically there are 3 hazards that we are going to consider today. The first one is the data hazard. The data hazard happens due to the dependencies between the two instructions. The execution of one instruction depends upon the completion of data access of the previous instruction. Let me show you an example to demonstrate clearly. The first is the add instruction, which uses 3 registers x19, x0, x1, and subtract instruction, which also uses 3 register x20, x19, and let's say x4. So the data in these 2 registers is added and stored in the x19 register. Clearly we could see there is a dependency between these 2 instructions, and the execution of subtraction instruction depends upon addition instruction. Now we could avoid the penalty by using several techniques. The first one is the forwarding or bypassing technique. Let me have an overview. This is time scale. We have addition instruction. Then we have 5 stages of pipelining: execution, memory, and write back. And in the next instruction cycle, we have subtract. Again, 5 stages of pipelining. Here we could see that the latch at the end of the execution stage of addition stores the result of x19, and we could directly transfer it to the instruction decode of subtract instruction, and don't wait for the whole pipeline to complete. The second way to avoid this penalty is by using code reordering, in which we could execute them out of order and increasing instruction per cycle IPC of the processor. So the second hazard that we are going to consider is the control hazard, which happens because of the decision on control action depends upon again on previous instruction. Here the branch determines the flow of control, and the instruction being prefaced depends upon the branch condition. For example, there are if and for conditions in C programming language. Let's take case of if x is equals to 0, then the instruction of these the execution of these instruction depends upon this condition. So we could use again we could use branch predictor technique to solve penalty for control hazard, and avoid the stall in the pipelining only if there is a wrong prediction being made. Now, if we again consider RISC-V architecture, then it predicts the branches not taken, and the instruction can be prefaced before branch without any delay. The final hazard that we're going to consider today is the structure hazard, which happens because there is a conflict of the resources being used by the processor. Again, going back to the RISC-V architecture, the load store uses data access, and the instruction fetch state has to wait for that particular instruction cycle for the fetching of the data. Now, this is the most important reason why for the pipeline data path we have separate instruction and memory data paths. So to summarize, the data and control hazards are the most common hazards that we see in our modern processors. Thank you.